Okay, so hello and welcome to this video lecture. So today we are going to have flexural stress problems. So for this particular problem, we have the layout of the wooden section is built up of two 75 by 75 millimeter glued on the lower side of the larger section, which is 75 by 150. So we can see it in the figure. So we are going to calculate the maximum bending stress of this 2.7-meter simple beam about to carry 3.25 kilonewton meter. Of course, the first thing we wanted to calculate is the neutral axis, because the neutral axis will be your basis in determining the value of the farthest distance, because we are referring to the maximum bending stress. So note that the formula involved in the bending stress is this formula, and C here is the farthest distance from the neutral axis. So we're going to compute now the location of the neutral axis. So the first step is to have a line anywhere in the section, wherever is your comfort. You may assume a line on the lower portion or on the upper portion or anywhere in this layout. So this time I'm going to consider the lowest portion as my reference line. And this is where you can measure your Y bar, wherein Y bar is the distance of the neutral axis from your reference line. And then we shall note here the distances. We have 75 for each of the width of this individual section, and the larger section has 150 height compared to the 75 of these smaller pieces of section. Then we are going to tag these composite sections by number. Of course, there are 3 areas here and 2 wherein there are 2 identical sections. So here I'll just label the 2 identical sections as 1 and the larger section as 2. And we will be involving this formula to obtain the Y bar. So a Y bar, or the total area times Y bar, is equal to summation of the area times Y's, or the vertical distance of each of those composite areas centroid up to your reference line. Okay. First, I'll just compute for the particular areas of this section. See, area 1 is 75 by 75. So we have 5,625 for one area. And then its corresponding distance is 37.5, or it is just the half of your area 1. Okay, so for area 2, we have 75 by 150 is equal to 11,250, and your Y2 as well is just the half of your height, or that is 75. So the total area, we have to multiply this by 2, and it will yield to 11,250, and we have the total area to be equal to 22,500 millimeters squared. Then we write now this formula, the total area times Y bar is equal to 5,625 times 2. There are 2 area 1 and then the Y1, 37.5, and then this one, 11,250 times 75. And we will come up with a value of 56.25 millimeters. Now, it is important to note that 56.25 will be referred to your reference line here, or the blue line. Then the next step is to compute for your moment of inertia. So it will involve here a transfer distances. Okay, so now that we have located the neutral axis, there are corresponding transfer distances of these shapes with respect to the neutral axis. Say we have D1, the centroid, and then the centroid of D2 up to your neutral axis. And this shall involve this formula that Ix is equal to the summation of I plus AD squared. So D here is the transfer distance. We can have D1 as the y bar minus y1. That is 56.25 minus 37.5. And that will yield to 18.75 millimeter. Now D2 is equal to y bar minus y2. And it will yield to negative 18.75 millimeters. So 18.75 is having a negative sign. Does not matter because it will just be squared later on in your formula. And then we now perform I bar. So we have 2 area 1 or I for 1. So each of the I bar is BH cube all over 12 plus 75 by 75, the area, and this is the transfer distance. So we add also the larger I, we have 75 by 150 cube all over 12 plus the area times the transfer distance 18.75. So we will yield to 34.28 times 10 raised to 6 millimeter raised to 4. Okay. So y bar and I bar were already obtained. So what is left in the formula is the moment. Okay, the moment force that will be produced by this 2.7 meter simple beam to carry 3.25 kilonewton per meter. So if we have a simple beam, we can right away derive the maximum moment by this formula, WL squared all over 8. So if we have a pin and a roller that is located at the far end of the beam, we'll just have to use this formula, and it is loaded by a uniformly distributed load. So that is what we call a simple beam, wherein we can use this formula for the maximum moment. So we have WL squared all over 8. So we will be having here 2.96 kilonewton meter for its moment or the maximum moment. Okay, so we are now ready to determine our maximum flexural stress. So we have this formula, MC all over I, wherein C is farther on top rather than the computed 56.25. So as we can see, we do not have a symmetry on the Y bar. So we'll just have to see or choose the greater value of the distance from the neutral axis, and that is actually on top. We have 93.75 millimeter for C. So by this, we'll just have to substitute it in the formula and come up with the maximum flexural stress equivalent to 8.1 megapascals. Okay, for the next problem, we have here a simply supported beam having a roller and a pin. We have a symmetric layout of the location of the supports, and then we have unsymmetrical loading. We have 4 kilonewton meter distributed load and 8 kilonewton concentrated at point B. So the cross section is B by 300 millimeters. So B here is yet to be calculated on the condition that allowable flexural stress is equivalent to 12.5 megapascals. Of course, having the flexural formula, we need to establish first the maximum moment of this beam, and then after which we will just have to relate to the cross section or the rectangular section in order to come up with the I, okay, and then B will be expressed in terms of the formula of I and also the area. Okay, so let's start. First, we have the shear diagram. Okay, so as we can see here, from leftmost portion, we have a rectangular shape here that is equivalent to 4 by 2, and that is going downward. So 4 by 2 is actually negative 8. And then the reaction is actually derived out of summation moments at both supports. So let us discuss first the reaction. So summation moments at point A, we have 4 by 8. Okay, so the overall dimension of this rectangular load is 8 meters. So 4 by 8 times the moment arm is 2 plus 4 RB, okay, plus 8 times 4. So perhaps this shall be negative. Okay, so that should be negative, and then we'll be having an RB of 24 kilonewtons. We do the same along the RB. Okay, so on B we have a negative rotation for the result of rectangular loading here. Negative 4 by 8 times 2 plus 4 times RA is equal to 0. And then we will have a reaction of 16. And then we are going to place now our reaction on the beam. Okay, so continuing with the shear diagram, from negative 8 a while ago, we have to push it upwards by 16 units, so that it will yield to positive 8. And then again, we are going to deduct here 4 by 4, or that is 16. So 8 minus 16, that is negative 8. Again, there will be a push here. But before we take the effect of this push, let us consider the counter between 24 and 8 at joint B. So therefore, if we're going to deduct 24 minus 8, that will yield to a positive 16. Okay, so it will yield to an upward 16. Okay, so negative 8, it will push back to a positive 8 here, because this will be pushed by 16 units. Okay, so we have 8, and then eventually 4 by 2 will close it to 0. So moving on to our moment diagram, we'll just have to compute the areas here. So the triangular area here is 8 by 2 divided by 2. That is obviously negative 8. And the same area will be added to that negative area. So therefore, it will just yield to 0 here. So there will be a point of tangency on your 0 moment. And then, of course, we'll just have symmetrical effect here. Okay, so negative 8. So in short, we have obtained the moment. Okay, we are now ready to determine the dimension B given this allowable flexural stress. And then we note that I is equal to BH cubed all over 12. And the maximum moment is negative 8. So you just have to substitute in this formula, equating it to your allowable 12.5 megapascal. So we come up with 42.66 millimeter width for this particular beam. So meaning this is the minimum requirement for us not to exceed with the allowable shearing stress, or allowable bending stress, I should say. We have 12.5 megapascal. Okay, so moving on to this third problem, we have a beam carrying the concentrated load. So the concentrated load here, as we can see, is expressed into P's. We have 3P, 12P, and another 3P. So it is symmetrically distributed on the beam at those points. And we also have here the beam cross-section as well as the dimensions, the web thickness, and the width of the flange. By the way, this is what we call the web, okay, and this is the flange. Okay, so the outer portion of the section is actually our flange, and this is the web. Okay, so to be able to determine the value of P with this condition, where allowables are given, we have a tensile flexural stress equivalent to 33 megapascal, and the compressive bending stress is equal to 67 megapascal. So if we have a positive moment, let us note that the boundaries are within this line, and that red line there is actually the neutral axis. So beyond that neutral axis, it could be either tensile or compressive. So if we have a positive bending here, okay, so the bottom fibers beyond the neutral axis is tension, and the upper portion is the compression zone. So for a negative moment, it will just be inverted. Okay, so the compression zone will be at the bottom, and your tension zone will be on top. Okay, so by that notion, we apply that by and by. Let us first compute for the maximum moment, or establish the moment diagram, and it will be in terms of P here. So we first note that our reactions will be 9P for both, because these are just symmetrical loading, 3P, 12P, and 3P. So all in all, we have 18 that will be just shared by these two reactions. So they have both 9P. And out of this, your shear diagram is established. So from the leftmost portion, we have 3P going downwards. So it will go down by 3P units, and it will stay until 9P will push it upwards, becomes 6P, and then no loading until this 12P will push it downwards by 12 units of P. So it will have a negative 6P. No loading, it will stay at negative 6P until 9P here will push it upwards, and it will become 3P, and no loading, and eventually this 3P here will close it to 0. Okay, so by this, we can also establish the moment diagram. And your moment diagram will be based on the areas here. So first, we have 3 by 1.5, that is actually negative 4.5. And then from that, we have 6 times 2.5 is equal to 15, and that negative 4.5 plus positive 15, that is, so this should be 10.5. Okay, so from 10.5, again, we deduct negative area here. 6 by 2.5 is 15. Okay, so 10.5 minus 15 is actually 4.5. And then it will, so let us correct that. That should be negative. And then eventually this positive area will close this negative 4.5 to 0. So as we can see that the maximum moment is 10.5, and maximum negative moment is 4.5. So moving on, we need to go over with the moment of inertia as well as the y-bar of this cross section. First, for the y-bar, we'll just have to consider here the bigger triangle or rectangle. So the bigger rectangle here is 100 as the base. Here it is. And 120 as the height. We're going to have the centroid of that from the bottom portion. By the way, I have chosen here the bottom portion for the y-bar. Okay. And then the half of 120, that is 60. That is for the whole rectangle here. And we still need to deduct these smaller rectangles. So that is actually the dimension of this is 100 minus 20, so that is 80. So they have the same width of 40 millimeters. So we have 2 times 40 times the distance of this centroid up to your reference line is from 20 plus 50, that is 70. So we divide that by the total area. So actually that is 100 by 120 minus 2 by 40. And that should be equal to 4,000. Okay. So y bar therefore will be equal to 40. And we can now work with our I. First, we have the larger one, BH cubed all over 12, and then 100 by 120. This is the transfer distance, okay? So if we have a 60y1 here, we have a 40, so we have 20. 60 minus 40 is actually 20, okay? And then we deduct the BH cubed all over 12 of those smaller portion. Of course, that is multiplied by 2. And this is AD, or area times transfer distance. So we have 70 minus 40 is 30, that is the transfer distance. So substituting the values, we have an I of 5.33 times 10 raised to 6 millimeter raised to 4. So after completing all of this y bar, I bar, and your moment, we are now ready to determine the maximum value of P. Okay. So basically, we have here the condition, the value of P, if allowable stress or flexural stress in tension is 3 or 33 megapascals. And your allowable in compression is 67 megapascal. So we start with this 33. Okay, so 33 will be your left hand side of the equation because that is the allowable for tension. So what are those tension here? So for positive orientation of the bending, your tensile will be at the bottom. And what will be your positive moment? That will be equivalent to 10.5 here. So that is the positive. And then the distance of the tensile is 40. So where's that? So it came from your calculation of y bar. Of course, your y bar at the bottom, or the distance at the bottom, is 40. And the remaining distance here is 120 minus 40, that is 80. So we note those distances. Okay. So we have 40 on the bottom and 80 on top. So if we have a positive one, where is the tensile? It is at the bottom. So we consider here 40 as your multiplier for C. So we are going to multiply this by 1,000 instead of 1 million because P here is yet to be calculated. The intention of this 1,000 is just for the meter unit to be able to become millimeter. Okay. So we come up with the value of 418.79 Newton. And then again, we have to use 33 for a tensile for negative. For negative bending, we have negative 4.5 as the value. And then, where is the tensile side if we have a negative bending? It is actually on top of your fiber. And the top fiber dimension is 80, so that will be the multiplier here. And then 1000 intended to convert your meter to millimeter. And then we just divide it by your I. And then therefore, this will yield to 488.58. So between these two calculations, we have to consider the smaller value of P, which is 418.79 Newton. Okay, so if that is chosen, then we will be having a safer value for P, wherein it will not exceed 33. Why is that we are choosing the lowest value or the lower value? Because if we are going to choose this one and then back calculate it, it will surely exceed your 33 megapascal limit. Okay, and now we proceed to the criteria of the compression, which is 67 megapascal. And then again, it will be your left hand side of the equation, 67, and then the value for the largest positive. Okay, we consider first the positive, that is 10.5 kilonewton meter or 10.5 P. Okay, so sorry, we should have to indicate that these are in terms of P. Okay, so we have 10.5 P times your conversion factor 1000 times 80. Why 80? Because your bending here is positive. Okay, this is 10.5 is a positive moment. We'll have a upward orientation where the tensile zone is at the bottom. The tensile zone is at the bottom. And if your tensile zone will be at the bottom, I think we should consider here 40 instead of 80. Anyway, still correct because we are on the compression side, should be on top. So we have 80. So your value for P would be 425.13. And then for the negative moment, that is 4.5 of P, we used the bottom dimension since your compression side is at the bottom when the bending is going downwards. Okay, so by this, we'll be having a value of 1983.94 Newton. Again, we are going to consider the lower value for a safer value of P. So I think this completes the problem. So thank you for listening and good day.